Okay, so watch carefully. On the left hand side we've got 20 ohms resistance, which is in series with the gauge, and as you can see the temperature gauge has started to move. Hello and welcome back to the channel. Last episode on the Capri was we found that we didn't have any temperature gauge, didn't have any fuel gauge, we had no electric fan. It was all going badly wrong. Car had stopped, wouldn't start again, basically overheated. This episode, what I've been trying to do is, and I'm hoping to show you, is testing these two gauges. Got all the dashboard out, as you can see, and I need to make sure that these gauges work off the car so that we can eliminate the gauges themselves to make sure that they're all good and I haven't got to start looking for them, rather than fiddle about for days on end at wiring and tracing this, that and the other. We start with making sure that the components that are supposed to work actually do work on the test bench. So this is what this episode is about: testing these two gauges, seeing if they work, testing them with a dummy sensor, and then hopefully with the real thing. Before we get to that point, a quick explanation about how gauges and sensors and everything works on a car of this age. First thing to remember, everybody gets really scared of electrics. Some people it's an absolute black art, they really don't want to get involved, they really don't understand it, and of course if you get it wrong it can be dangerous, you can cause a fire, and that's not what you want in your car, of course. But to be reassured, everything that it works in this car is all fundamental foundation electrical theory. We've got a battery, in other words a power supply of 12 volts. It supplies electricity to the car, and it supplies all these gauges and lights and switches and sensors, and the basic fundamental principles that it's using are what's called Ohm's law. And Ohm's law is the relationship between voltage, current and resistance, and how those three things can be made to interact with each other to actually get electricity to do work for us. Basically that's the basic fundamental thing that we're trying to do. Now the two gauges and the fuel sender are electromechanical devices. In other words, they are fed with electricity, and the electricity does some work and converts that into mechanical energy in the form, in this case of a gauge, of a needle, and with the sender, the fuel sender, a float arm. In the case of the temperature sensor, that is purely a temperature sensing component. It heats up and the resistance, electrical resistance inside the component changes. When you feed a piece of copper wire with electrical current, the first thing it does is it heats up because of resistance. We can use that heat to our advantage, and we can use the heat to change the molecular structure in a piece of metal to make it bend under heating. And if we control that resistance with the voltage and the current that we're adding to this component, we can make that bend more or less. And basically that's what's happening in the two gauges. We're feeding it with electricity. They have a coil of wire which heats up, which is wound round what's called a bimetallic strip. That bimetallic strip then heats up and it starts to move a lever, which in turn moves the needle. And the amount of resistance that is required to heat that up varies with the sender sending you the information from the fuel tank or from the temperature sensor, based on the amount of temperature we have and based on the amount of fuel we have. There's a resistance in those two sensors which limits or controls the amount of electricity going to the gauge, and therefore the more electricity you have, the more heat you will have around that coil, which will then move that needle. Not going to go too much more deep into that than I have to, because I'm probably losing people already. Suffice to say, the relationship of voltage and current and resistance is basically how these things work, and pretty much everything in this dashboard is pretty much like that, save for the oil pressure sensor, which is a direct sensor with an oil pipe to it which is connected to the engine block. Everything else is pretty much electrically controlled. Oh, and the speedo, of course, is a mechanical speedo with a mechanical drive. But the rev counter, the voltmeter, all the switches, the fans, the lights, the wipers, all of that, the fuel gauge, the temperature gauge, they are all electromechanical devices, and they all work off the same basic principles of Ohm's law. Right, so we've got the dashboard on the bench, and I'm going to, I've got a fair bit of tidying up to do. Some of this plastic fascia covering's all got to be repaired somehow, because it's all sort of got heat damaged, I think, and it's all buckled and perished. So I'm going to try and get that off, but basically what I want to do first is sort out these two clocks here. So what we're going to do is we're going to rig them up to a power supply, variable resistance equipment, to basically simulate the temperature sensor and the fuel sender to see if they work, basically, with them out of the car. So I'm going to get the whole clock unit off the back of the dash, and that's pretty much easily done. We've basically got 1, 2, 3, 4 screws, which takes off the whole lot, and I can get rid of the main part and give us a bit more room to work, and we'll get it all rigged up. This, if you remember, this is the voltage regulator, and here are the back of the temperature gauge, and here is the back of the fuel gauge. This side is the voltmeter, and this is the pressure gauge, which is direct feed from the engine block. We've got the rev counter there, and we've got the speedo there. Okay, so I think the first thing we need to do is probably take this glass off and clean it so we can actually see what the heck is going on, because that is pretty filthy, I have to say. That's the back of it, as I've just shown you. So I'm just going to unscrew that and give that a clean, and we'll stick it back on so we don't do any damage to any of the needles or anything like that. Anything drops in there and sort of damages the clocks. I'm expecting under there to be pristine. Tiny little bit of moisture on the trip button there, I can see inside, but I'm going to take this off first and then we'll go from there. That looks way better, and now I can read much better the clocks through all that dirt, which is now gone. Right, so we'll get it set up on the test equipment, and then we'll go from there. Okay, right, now we've got the first part of the setup going. Now what we're going to do is we've got to figure out whether these two gauges actually work or not. There's a fair chance that they have been fed with 12 volts for a fair period of time, in which case it's quite likely that they've been blown. And the reason for that is because the gauges themselves are designed to work, I believe, Ford gauges of the period 50s, 60s, 70s, before solid state and electronics came in. These Ford gauges were designed to work off of a supply of about 5 to 6 volts, so effectively half battery voltage. Now, because the battery on a car of this period was 12 volts, they needed to find a way to supply these gauges with the battery voltage that they got in the car. Not only that, with the battery discharging and charging as the engine is running, for the lights are on, and then it's charged up when you start it, and then it stabilizes again. You've got fluctuations in voltage of that battery throughout the use of it during the car, while the engine's switched on and the car is being used. So that's where the voltage regulator comes in. Now, the voltage regulator is basically, it's mechanical, working off of electrical principle of heating and cooling, a bimetal strip. And the way that's done is there's a bimetal strip inside here. One end of it is connected to 12 volts. The other end of it has got a contact on it, and around that strip is a coil of copper wire. And when that coil of copper wire is fed with electricity, the wire heats up, it heats the bimetallic strip. The strip starts to bend and it makes the contact on the other end of the regulator, which is this thing here, this terminal here. So at the moment what I've got is, if you look over here onto the left, I've got the power supply, just 12.2 volts, something like that, and it is connected on to the positive side, the 12 volt side of the regulator, and it's actually got written on the Bakelite here, ignition, IGN. So that is your switched feed from your ignition switch, 12 volts, and the other side of it is the open side of the contact. Now, the negative return for the dashboard is this post here, which is basically between the two terminals for the temperature sensor, and I'm going to connect that up to the power supply, and you will see in a second what happens. Now currently, if you look at my test light, I've got nothing lit on the test light whatsoever. As soon as I make that connection, the light comes on, and after a few seconds you can see that it's actually flashing. And what's happening inside that regulator is the bimetallic strip is heating up, it's making a contact which gives us a flash on the test lamp, and then it cools down again and heats up and cools down and is constantly opening and closing. And what's happening is that the 12 volts is being regulated down to about 5 to 6 volts, but we cannot measure that because the multimeter is a digital multimeter, and all it does is it's just too slow to pick up the measurement of the voltage. If you were to do it with an analog meter, what you would see would the needle on the analog meter would be flicking backwards and forwards from 0 to more or less around 5 or 6 volts. But to see an accurate reading of that voltage, you would need an oscilloscope. Now I don't have an oscilloscope, and the only way really to, other than using an oscilloscope, the only other way to really find out whether this is working properly is keep an eye on the flashing light. Now if the flashing light is a regular light like we have here, then we can fairly safely assume that the regulator is working properly. If it was an irregular flash and it was stopping and starting all over the place, not sure whether it wants to light up or not, all that sort of stuff, then there's a fair chance that the contacts of the regulator, the contact points, are either burnt or they've lost their continuity or the conductivity, and they're just basically worn out. And of course, if you've got nothing flashing at all, then the voltage regulator is doing absolutely nothing. So at the present moment, I can be fairly sure that this voltage regulator is working and doing what it should be doing. Right, so the next step of the process is to introduce some kind of resistance to simulate the temperature sensor heating up and cooling down. So what's supposed to happen is that the temperature sensor is in the cylinder block, or in the in our case in the inlet manifold, but somewhere in the engine where it's going to be into the water jacket. And as the water heats up, as the coolant heats up, what's happening is the resistance inside that sensor is starting to change, and it starts off at high resistance, so therefore not much electricity can pass through it. And as it heats up, the resistance drops, and as the resistance drops, more electricity can be allowed past, and therefore it creates a circuit which enables the gauge to start moving. So the more electricity that the gauge gets, the further it will move. So what I've got here is I've got a resistance box with lots of different resistance, variable resistance knobs on it, from 0.1 up to times 10,000. So I can actually get 100,000 ohms resistance through this resistance box, depending on which knob that I use. Now, as I've got it at the minute, I'm on the times 10, and I'm on 2. And if you look on the gauge, I've got 20.6 ohms, so we're not going to worry too much about 0.6 at the moment. We just want to see if this all works, and we're basically trying to see if the gauges work. Now, so at the moment I'm measuring 20 ohms. So I'm going to connect this up to the gauge, and we can measure or change the resistance. We've still got our supply coming into the regulator. I've added in a green wire from the the other side of the regulator that goes directly to the back side of the gauge itself. And then I've got a yellow wire coming off the other side of the gauge, which is going to go to the resistance terminal on here. And then this side of the resistance terminal, variable resistor, will go back to negative on the power supply. Okay, so watch carefully. On the left hand side, we've got 20 ohms resistance, which is in series with the gauge. And as you can see, the temperature gauge has started to move, and it's gone up to about a quarter of the way up. If I increase the resistance, very, very gradually, you'll see the temperature gauge drop back. So I'm increasing the resistance, therefore less electricity can flow through the gauge. And if I add 40 ohms, I've got less again. If I go the other way, up to 10, that's now 10 ohms, and I've got much less resistance. You can actually see the temperature gauge is moving. And the good thing about that is I know that temperature gauge is good. Happy days. And we can do exactly the same with the fuel gauge. So I've swapped over the terminals, so I've now got the input from the regulator onto the back of the fuel gauge here, the green wire. On the other side of the gauge, I've got my yellow wire going to my resistance box down here, negative back to supply, negative off the back of the dashboard, and the 12 volt supply to the regulator. Nothing's changed there. And if I just do my test light, there's my light coming on. Now if I turn this over, we can see the front of the gauge again. And this time we're looking at the fuel tank gauge down here. I'm on 10 ohms here, so I'm just going to increase that a little bit, take it up to 20 ohms again. And when I switch on the supply, just pay close attention to the fuel gauge needle. And it's moving, which proves that the gauges are good. We've got 12 volt supply to regulator, regulated supply from the back of the regulator to the gauge, 20 ohms, and just under half a tank of fuel. If I drop that to 10 ohms, you can see that the fuel tank gauge is climbing again. So it works exactly the same way. Less resistance gives more electricity, therefore the gauge moves further over. And if I give it no resistance at all, you see it climbs right up. No, we don't want to do that because we don't want to overpower it. If I drop it right back, it comes back down just gradually up to 40 ohms, and now the fuel tank gauge is dropping back. So the next question is how do we know what sort of resistance we need to be adding into the gauges to make them work properly? And the only way to find that out really is to measure the two devices which have the variable resistance, and that namely is the temperature sensor and the fuel sender. So let's give that a go. So we'll start with the temperature sensor. Now I've had to buy a new sensor because when I took the old one out, it fell to pieces, which sort of suggests that that was actually faulty to start with. So the top part of it's actually come out. So I bought a new one, and that's this one here. It looks like it's pretty much identical, except this has got a screw thread on the top rather than just a little terminal, a slip-on terminal. And what I'm going to do is I'm going to measure the resistance of it when it's cold. So at the moment it's completely cold. And if you look over there on the multimeter, we can see that we've got 232 ohms coming through that temperature sensor. Now the terminal where the red crocodile clip is, that is the terminal coming from the gauge. So that is the the feed from the gauge to the sender itself, and then the crocodile clip, the black crocodile clip on the bottom, that is where the sender would be earthed or negative returned through the engine block back to the battery. Now, as I put that in some hot water, we can see that the resistance is actually going down, and the temperature of this water currently is something in the region of 70 degrees. We're now up to 77 degrees and we're down to 44 ohms resistance. So remember, as the heat goes up, the resistance goes down, more electricity can pass through the gauge, which allows the gauge to increase indication of increased temperature. 85 degrees is somewhere around about when the thermostat would start to open in the engine, and we're now down to 34, 33 ohms on the meter. So the gauge would continue to rise. Running temperature would be somewhere in the region of, I suppose, around about between 98 and 100 degrees, maybe a little bit more. I'm about to boil over 98 degrees. We're down to 23. Now, we're not going to get full deflection on the gauge with 23 ohms, so we're about operating temperature of the engine right now. So what you'd see on the gauge probably would be around about halfway, 2/3 the way up. And of course, what we've got to do now is we've got to try the sensor, or the new sensor, with the gauge. So I've got about 90 degrees. Let's put the sensor into the water and see what happens. Getting close to boiling, and hopefully you can see that our temperature gauge is rising, and the temperature gauge is working as expected, and we've proved everything works as it should. Okay, so we're on to the fuel sender. Now, this is the one out of the car, of course, and there is an immediately obvious problem, and I don't know if you can see, but inside the float on the end of the fuel sensor we have some fuel. If I just shake that around, you can see there's fuel in there. Now, when I took this out about 3 or 4 days ago, that was pretty much half full, and it's slowly evaporating out of what must be a little hole here. This is where it must have been melted for some reason. Don't know why, but I'm going to have to get the rest of this fuel out of here, because it's never going to float. It's always going to be, or it's never going to float in the right place, I should say. So the idea is that this floats on top of the level in the tank, and the level of fuel in the tank, and moves the arm up and down, such like that. And inside here, where the arm is connected, is a variable resistor, which is basically what I've been doing with the little black box. There's a terminal on the outside which goes into the resistance box in here. There's a whole coil of wire, there's a wiper, and that wiper is connected to the other side of the sender, which basically goes back to negative on the battery. And it's exactly the same as what I've just used, showing you on that box. And the more this moves, the more or less resistance you get, and therefore the more or less electricity it passes to make the gauge work. Right, so let's test this and see if it works. So I've got my multimeter connected to the terminal that comes in from the gauge through the resistance, which is inside this little box here, and then it earths or returns negative back through the body of the actual fuel sender itself when it's connected to the tank, and the tank is then bolted to the car. So that creates a circuit. Now, at the moment it's as it would be in the car. So this is the pickup pipe and this is your float. Okay, now if you look at the multimeter, we've got basically an over limit. In other words, we have got high resistance, no continuity at all through that sender whatsoever. Now what we should be seeing, and I've googled this, is somewhere in the region of, when the fuel tank is empty, somewhere in the region of about 70 ohms. So 70 ohms would equate to higher resistance, less electricity, and therefore the gauge needle would be on on the 0 mark or close to 0, because it won't be getting much electricity. The more fuel you put in, the higher the float will rise and the resistance will go down inside the sender, and consequently more electricity can pass through the gauge and allow the needle to go up and onto the full mark. So as this moves up and down, what you should be seeing is some kind of movement on the multimeter, and we're getting nothing at all. And very occasionally we are getting something happening. Now it's come up to 400k, and now it's gone off. Now if I move this arm, it's gone completely. If I now press that arm further away from me, in other words, I'm making the resistance actually work inside, I've got 72, 73 ohms. If I raise the float, you can see the resistance is actually dropping till we get to somewhere about 10 or 11 ohms. That's as far as it will go up, and that would constitute a full gauge. If I pull the arm away again I've got no continuity. So I've got a problem inside this fuel sender where the wiper of the resistance is not actually touching the coil and the winding of the resistance all the time. If I push it away all the time, then I can get the resistance readings that I'm looking for, and those basically they do check out to what you can find online. Now because I was getting a consistent reading from top to bottom, I'm pretty certain that the coil is actually good. If I was moving the arm and measuring the resistance and it was stopping and starting, sort of dropping in and out, I could sort of deduce that maybe the coil is worn out and broken. And if I was getting nothing at all, whatever I did with the arm, then certainly it's definitely broken. So I'm sure as I can be that the coil in there is good. And I didn't really want to take this completely apart because it can be quite fiddly, and also it's quite delicate, so I didn't want to break anything if I didn't have to take it apart. Now it's got one electrical connection, which is the connection where the crocodile clip is. That is the wire coming from the gauge, and then it earths back to battery via the body and the rim of the fuel tank sender itself, where it locks into the fuel tank. And if you undo that nut on the end of that terminal, this whole thing comes away. And what it's doing, it's relying on contact. The body of this is relying on contact with the actual sender lock itself, the plate, to earth through the plate, through the tank, back through the car chassis, back to the battery. And what we need to be, really sure is that there is a good connection between this part and this part. Now, if you remember, what was happening was as I was moving this up and down, I had to bend or push on the wire, on the lever, sort of prematurely to make it actually read. Now, at the moment, I've got 67 ohms, which is where it's at the bottom, and if I lift it, it goes to about 10, and I'm not having to do anything other than lift it up and down. And what I've done is I've basically, these little tabs here, I've basically given those a little bit of a squeeze out and make this all tight, because it's relying, that wiper that's inside there that's running on that coil, it's relying on the wiper frame, the actual pivot, to earth through the body of the box, and then in turn through the cap and into the tank. So what I've done is and there's a spring in there which is basically keeping everything tight, and that was all sort of quite loose and just a little bit vague. So I've tightened everything up, and I've also given that a little bit of brake cleaner, and where I can with a sort of like a brass wire brush, sort of given a bit of a clean around, so that if I get close in, I don't know if it will focus, but you can see there that little rod that's coming out of the box. There's one on the other side as well. And that is basically, that's where it's relying on earthing the unit through the float arm. So it's pretty tenuous. But I've got it now so that this is tight up against there and is earthing. Obviously the terminal on the inside is insulated from the body, otherwise you'd have a short. So that the variable resistor is actually working. So if I just lift up and down the rod, and the arm, you can actually see everything's moving exactly as it should be. Now what I might do is I might actually solder a piece of wire from the resistance box itself onto this pipe here, so that there is a clear path between the box and the pipe, which is basically the body of the actual cap, the actual twist cap that goes into the tank. And then I know that I've got a good connection between the box and the body, and then all I've got really is just relying on here, and it's relied on this for 50 odd years, so there's no reason with a good cleanup as I've done it's not going to it's not going to fail again for another 50 years. So here's hoping. Now the other thing is, if you remember, the actual float itself has got a hole in it, and when I started poking around I found that the hole got bigger. So clearly somebody has actually tried to seal this up with some kind of epoxy in some time in the past and has not been successful. So I thought, well, you know, how can you get adhesive or glue or filler that is going to be petrol resistant? And I thought, I'm going to be doing this job again and again if I don't do it properly. So I thought, well, I'll see if I can find another float. Now I can find another float, but unfortunately it's not this shape. This is like a lozenge shape. All the Ford ones and Escort ones and the Cortina ones I think are all exactly the same, but do you think I can find the float on its own? Not so far. So basically you can buy the Smith's one, which you can find in Minis and British Leyland products, but of course this one is round whereas the other one is lozenge shaped. So the thing that it sits in is only just a wire arm which I can easily bend and manipulate to basically fit this float. But of course I've got to put it in the right place, because if you can imagine, when that's in place on there like that and I put this one in place of it, I've got to make sure that the height of that float to the bottom of it from a fixed point is the same height as this is going to be. So I'm going to have to bend the arm accordingly and basically calibrate this arm to fit this shaped float. Otherwise what's going to happen, because the diameter of this float is much higher, or much wider or greater, the float, when it sits on the top of the fuel, is actually going to end up higher, if you can imagine. So I've got to basically manipulate this wire to put this float in, but it will do the job once I've got it on. All it's got to do is just basically float on the fuel. It's just got to float on the fuel in the right place. I hope that's clear, and yeah, pretty much it. I'm pretty happy with the fuel sender as it stands. Certainly saved myself quite a few quid having a repair, or trying to repair it and get it working again, and so far I'm happy with it. Just the float to do, and then it can all go back together. So now what we can do is, with the power supply connected to the gauges, connected to the fuel sender, watch the tank gauge as I operate the float. The float's as far up as it can go, and up goes the gauge. That's that bit done. Happy with the fuel gauge. So that is gauges, fuel sender, temperature sensor, all tested and all working out of the car. Remember that bit, it's all done off the car on the bench. The next challenge is going to be putting all that lot back together. We've got lots of wiring to sort out on the back of the dashboard. I'm hoping I can remember where it all went. I did take some photographs before I unplugged it, but a lot of it is self-explanatory. And I do have a wiring diagram with colour codes, and all the wires are in good condition from the point of view of being able to read the colours. So shouldn't be too difficult a task. But I'm going to get the dashboard back in on the next episode. The fuel tank and the fuel tank sender back in, put the temperature sender back in, and then we can try all of that stuff again. The fuel tank sender clearly will work, or it won't work straight away because we put fuel in it, but I'll have to run the engine, of course, to get the temperature sender to show that it works. But I'm fairly confident that it's going to work. The only thing it can be now, if it doesn't work, it's going to be wiring in the car. But I will check the continuity up to the dashboard and then to all the different bits and pieces that we need to check. And then the other thing that I've got to do is it's got to have this radiator electric fan sorted out with I think probably a new thermostatic switch. So that's all happening in the next video, and if you want to have a notification of when that's going to take place, then click the subscribe button. It's free to become a subscriber to our channel. It helps our algorithm. More people we get, we're getting very close to 1,000 subscribers. I'm getting quite excited about that. It's, you know, small things and all that, but yeah, I think as of today we're on 949 subscribers, so I've got 51 subscribers to go. Are you going to be one of those 51 to just get us tipped over into that 4-figure subscriber count? It would be great if you are. Please help us do that, it would be great. If you like the video, then click the like button. If you want to share the video to some friends that have got a Mk1 Capri that might be interested in what we're doing. This one's been a little bit of a tutorial type of thing, not much fun perhaps for some people, but maybe interesting for others to understand how these things work. But certainly share to your friends if you've got people, like-minded people that want to know about this stuff. And what we've done today is relevant for all 70s cars, 80s cars, 90s cars as well. Things started to become electronic after about the 90s into the 2000s. But yeah, anything 60s, 70s and 80s, definitely this is all relevant stuff. They didn't really change much. They didn't really reinvent the wheel for many years. It worked and it was cheap and it was easy to use. So everything is relevant there. If you'd like to make any comments on what we're doing, that'd be fantastic. And above all, if you want to keep up with our mechanical adventures on our other vehicles that we've got in our fleet, then by all means, keep checking in, click on subscribe, and be great to see you. Till the next time, take care and bye for now.